Good day. My name is Vaagn, and here is Tigran.
Hi, my name is Tigran Gevorgyan.
We're gonna talk about HTTP Time Bandit. But before we start our talk, I have one thing to ask. This is our first talk at DEFCON, so don't be nice to us. Be very, very, very gentle to us. Please. Thanks. So, about us. Tigran and I work for Qualys. We break stuff for fun. Sometimes we fix them too. We are interested in time travel, and we'll talk about that a bit later. And we both love to try. We do triathlons. So, what we're gonna talk about? The presentation, short but effective maybe. You will judge by leaving the room or not. It's gonna be about another application layer DOS method, and we'll then show you the tool. We'll go through some stats, and we'll talk about what are good or bad uses of the tool or method, and then we'll glance over the defense against this method. Why? Why do we do this? It's obvious, because we wanted to have time machine. We couldn't buy any on eBay. We could, but it was similar to what you see on a screen, and that really doesn't work. So we thought we will make our own time machine, and I think we succeeded. The time machine that we have does one thing, and does it well. It can give you the future state of your web server given the resources you're gonna push on it. About it a bit later. So we're gonna talk about application layer, DOS tool or method, and for us those tools in application layer are of two different kinds. There are some that are not that smart, and another group that is a bit smarter. Non-smart approach is just pushing a resource over and over and over and over, hoping that the resource will die. And then you do that from multiple instances, and it works. But that doesn't have feedback sometimes, and load is near symmetrical. Smarter bots, like things like slow LORI, slow HTTP test, PKI abuse, and whatnot, they are smarter and they are asymmetrical in nature. Our proposed method is gonna be striving to be asymmetrical.
So how do we do this? So the point of this tool, the information from future, is picking the resources out of all the available ones, picking the ones that are most painful for the server. While people say, oh, servers don't feel pain, we all know they do. So how do we do this? We spider the website, we compile a list of the resources, and then we start measuring certain things, for example, the download speed or the start to download time. And what this gives us is a lot of data. And what deals very well with a lot of data, and that's statistics. So we use statistics to filter through the data. We calculate the average of all the download times. That gives us a baseline. What is a normal transfer time? And then we can tell, oh, these resources are slower or faster. So we used to formalize this. We used mean as the measure of central tendency, and we calculate the standard deviation. The resources that have high standard deviation, that means that they are inaccurate in terms of they can be fast or they can be slow, but we can't really tell. So we throw them away. We select resources that have slower download times or start to download times, and we think that this is related to CPU load. And the reasoning is that all the transfer delays are the same for all the resources, the network related ones. And so if some resource has higher transfer time, that must be resource specific, and that makes it interesting. So this, for example, is a chart of resource download for a website. And you can see that the majority of resources fall close together in some middle range. There are some outliers, some fast outliers and some slow ones. And the ones that are interesting are the slow ones. The question is, what causes these resources to be slow? Is it the CPU load, or is it just a slip somewhere on the page? So a small demonstration, and not to anger the demo gods, we did a video. Okay, so here the tool is running against a locally hosted web server, and when it's done, it generates a list of URLs with the measurement mean, the standard deviation. While this is nice, it's not very, very useful. Instead, the tool can be instructed to output all this information in an XML. So here we see the resources sorted by their download speed in increasing order. So the resources, the HTML resources down at the bottom are the fast resources, and the PHP resources are near the top. And this is because PHP requires the PHP interpreter invocation, which takes some additional time. And the resource at the top is some artificially made pi calculation, which understandably takes a long time. And so XML is very nice because it can be fed into some other tools. And I have one example, which is an XSLT that transforms this information into something that can be visualized. So you'll see a scatter chart of download speed and standard deviation. And there are 4 quadrants here. The top quadrants, 2 quadrants, they are the resources that have high standard deviation, which means that the measurements were inaccurate. So since we cannot trust these resources, we throw them away. Instead, we concentrate on the resources on the bottom half. On the right side, these resources are fast resources and consistently so. So they are not bottlenecks. Instead, we concentrate on the resources on the lower left quadrant. And closer to the 0 point, the better, the painful the resource would be for the server. The tool also can generate data for visualization in other means. For example, the next one, whenever it comes, the tool is instructed to generate graph.vises.language graph. So here you can see a small website with transitions, and each transition is marked with the transfer time. So slowly resources could be highlighted. I didn't do a good job here, but the capability is there. So next, the tool is going to scan a real website built with a concrete CMS. And so we give it the URL to start with, how deep into the web site to go into, and how many measurements for each resource to take, and write all that into concrete.xml, which will be processed later. So once it's done, it's crawling right now, so once it's done, it will generate the XML. And then what can be done with this XML is, again, feed it back into the tool, which will correlate and find out which resources are slow in its opinion. And it picked some PHP resources out of that. And so it will start sending parallelized requests to these resources and measure whether some service degradation happened. And it will output what was the original measurements and what were the new ones. So by looking at these deltas, you can figure out whether this is truly a CPU heavy resource or not. Now a bit about this asynchronous nature. So this slide shows 3 screens. The top one is the top utility output of the web server. The bottom right one is the client. So you can notice that the client has about 9.5% CPU usage, and this is mostly because of the recording software. And the server has 0. So on the bottom left, I'm launching the tool 5 times to request the most heavy resources. And the load on the client side, it was 9, it goes up to 9.5%, so negligible. But the load on the server side goes up to 82%, which is, asynchronous in my book. Okay, so this concludes the demo.
Now that we saw the tool, let's talk about what can be done with it. You can use it for the good of the humanity, as a QA tool, for example, or to figure out if you are vulnerable to attacks described a minute ago. By just going in and taking all those CPU hogs and debugging them or getting rid of them, rewriting them. Or you can use it for bad, which is almost what Tigran showed 2 minutes ago, where he paralyzes the worst resources and tries to see if degradation happens. Imagine that being all automated, and one click, bam, you go find the worst resources and then do more analysis by figuring out which ones are the worst in real life, which ones degrade, and then you push them even more. And then, of course, there is the ugly, which is the bad but distributed, basically. So that is what we have right now, and what we were thinking of on adding on the tool or method is a couple of tweaks. One would be the measurement of degradation, more precise measurement of degradation in parallel testing, which will go into nuances like understanding load balancers. We don't know how load balancers would behave right now, how our calculations will be affected by load balancers. Those things need to be worked out. Then we have a couple of other things that would be nice to add, like SQL wildcard injection into forms that we think are search forms, are in any way are fed to SQL query. And then another thing would be figuring out if state reset is pricey, to see if when you're forcing an application to generate new tokens for session ID or whatever, it takes any CPU load. That has to be calculated, estimated, or guessed, or doctored. Now let's talk about defense. Well, what can be done on the defense side? Load balancers are probably a good measure here. Our guess would be non-sticky mode would work here. And of course, use the tool or similar tools to identify and fix memory, DB, CPU hogs, make your application work smoother, and be less vulnerable to this attack. Slide deck has a reference number 1, which has a link to a very simple mode security setup that most probably going to cover 90% of cases. It's done by some other guys, but we find it's effective. And then there is one more thing that Tigran thinks can be done.
So I'm lazy, right? If I can offload something to the computer, I prefer that. So the idea here is to design a mode security extension that will keep in track of the website usage, meaning it will keep track of what resources, the chain of resources that was requested, the response times that were witnessed and all that. And it will track and tag out of place requests. For example, if a resource is requested all the time through some chain of events and this resource is requested immediately, that would warrant some special consideration. Same goes for state coherence checks, where a resource is always requested with some state, and now a request comes in without a state, that's an indication to pay some close attention to that as well. So I think,
yeah.
With that, we thank you.
We are in time. Thank you very much.
Thank you.
And thanks to Sean for setting up the lab for us.